Welcome back to Summarize Science. When we think about training a powerful AI, we often imagine a supercomputer crunching numbers at full throttle 24/7. The conventional wisdom has always been that to train these complex models, you have to update every single part of the AI's brain or neural network at every single step of the process. But what if that entire approach is fundamentally inefficient? In a fascinating new paper, researchers challenge this core assumption with a method they call Drop-Muon. The idea is surprisingly simple. Instead of tweaking every layer of the network in each training step, you only update a randomly chosen subset of the layers. The other layers are temporarily frozen, left untouched until a later step. Now, you might be thinking, doesn't that slow down learning if you're not updating everything? That's the counterintuitive part. This is where the update less part of the title comes from, and it saves a massive amount of computational work. Think of a neural network like a series of dominoes. To figure out how to adjust the first domino, you have to calculate the effects all the way from the last one. By deciding to only update from the middle onwards, you get to skip all the calculations for the first half, saving a huge amount of time and energy. And this is where we see the converge faster part in action. This graph is the key takeaway of the entire paper. The plot on the left shows that Drop-Muon, the orange line, sometimes takes more training cycles, or epochs, to reach a certain accuracy. But look at the plot on the right, which measures real-world wall clock time in seconds. Drop-Muon consistently gets to the same accuracy level significantly faster than the standard method, which updates everything. It's like a more fuel-efficient car. It might make more stops, but its total travel time is shorter because the stops are so much quicker. The researchers found that this wasn't just a small improvement. In their experiments, Drop-Muon achieved the same accuracy up to 1.4 times faster. To put that in perspective, a training run that would normally take 14 hours could be finished in just 10. For the massive models that take weeks or months to train, this kind of saving is a game changer. What's really compelling is that this isn't just a clever programming trick, it's backed by rigorous mathematics. The researchers proved that the old method of updating the full network is only the best strategy under a very specific and highly unlikely set of conditions. In almost every other practical scenario, their lazy approach of updating a subset of layers is theoretically the more efficient path to a solution. So, let's recap the big ideas here. First, the long-held belief that we must update every part of an AI model at every step is often suboptimal. Second, the Drop-Muon method provides a simple and effective alternative: update less to converge faster. Third, this approach is grounded in solid theory and proven with practical experiments, showing significant speed-ups. This could fundamentally change how we train the next generation of large-scale AI models. It means we could potentially train more powerful and complex AIs with less time and less computational cost, accelerating the pace of innovation across the entire field. It's a powerful reminder that sometimes the smartest way to work is not harder, but more efficiently.